Hello and welcome to our Wednesday webinar from the International Center for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, sustainable-carbon.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration on the website. Please do type in any questions in the questions box as we go along, and we'll answer them at the end of this webinar. The subject for today's webinar is the resilience of coal-based industry in the transition to net zero, presented by Greg Kelsall. Over to you, Greg.
Hi, thanks Benedict for that introduction. So I'm going to talk about the resilience of coal-based industries in the transition to net zero. It's a study that's been carried out by the International Center for Sustainable Carbon on behalf of the International Energy Agency's Coal Industry Advisory Board. So I'd like to acknowledge the input from colleagues at CIAB and supporting organisations in putting it together. So presentation outline, I'll look at the importance of heavy industries, look at how heavy industries can begin their journey towards decarbonisation, and particularly look at the role of coal as part of that journey. Look at carbon capture, utilisation and storage as a key enabling technology for coal to maintain its role, and then to wrap up with some key messages. So looking firstly at the importance of coal. Heavy industries are really integral to our way of life. If we look at concrete, for example, it's the second most widely used material on Earth after water. We produce around 4.1 billion tonnes of cement per year at the moment, which goes into the production of coal, and that could increase through to 4.5 to 5 billion tonnes per year by 2050. It forms much of our global infrastructure, including buildings for use in roads, bridges and dams, and is often reinforced with steel. So steel, currently produced at 1.8 billion tonnes per year, it's the most widely produced metal material, is used in infrastructure, used for vehicles, used to make most of the tools to actually make a lot of the products that we use. Aluminium, this is a lightweight material. Primary aluminium is currently around 95 megatons per year, and this is forecast to increase by as much as 50% through to 2050, largely because of its lightweight properties for the manufacture of lightweight electric vehicles, to produce aluminium packing to replace single-use plastics, and in its use to produce renewable goods. So if we look at solar PV cells, for example, solar PV panels are 85% aluminium. Chemicals is the other key foundation industry that I'll look at today. So ammonia, for example, this is produced at around 180 megatons per year at the moment, largely for the production of fertilizers, and we produce 400 megatons per year of chemicals for the production of plastics. These are truly ubiquitous materials. They're used in virtually all the products that we produce, and it's difficult to envisage how they could be replaced, certainly in the near term, because of their key properties. So concrete, as a mass-produced product, it's difficult to envisage how it could be replaced in building materials. Steel, because of its lightweight, because of its weight and strength and low cost. And chemicals, so plastics, they're very lightweight and difficult to replace. The challenge for heavy industries is that they're referred to as hard to abate. And by this I mean that we need high temperature heat for their manufacture. So this is used in many of the industrial process steps within heavy industries. It's difficult to replace fossil fuels to produce that high temperature heat by electrical heat, which isn't really cost effective or practical at the moment. So fossil fuels enabled by carbon capture and storage or fuel switching to hydrogen on biomass could be the preferred solution. Another factor is what I've called process emissions. By this I mean that a lot of the CO2 emissions produced within heavy industries are inherent to the manufacture process. So looking at cement, for example, around 65% of the CO2 emissions result from the conversion of calcium carbonate to lime. And there's no real way of avoiding that. So carbon capture and storage, again, seems to be a good way of dealing with that. Also some opportunities to switch to alternative raw materials that don't contain carbon. The third issue is the long life of capital assets. So typically these last for 30 to 40 years. And so early retirement of them would be costly to the global economy. And then finally, trade considerations. These materials, these heavy industries produce internationally traded commodities, which makes the introduction of new technologies hard to introduce unless it's done on a global basis to provide a level playing field. So just looking at plant ages, for example, so both iron and steel and chemical plants typically have lifetimes of 30 to 40 years. This chart here shows that around 85 to 90% of the global fleet is less than 15 years old. And this is an average of existing plant lifetime and looking at the refurbishment lifetime of steel plant, where they typically go through a refractory relining every 25 years or so. So taking an average of those, plant lifetimes are around 15 years. The Asia region accounts for a very large proportion of this, particularly China, and here coal is an important fuel. For chemicals, plant lifetimes are slightly less, around 25 to 30 years, and are more evenly distributed throughout the globe. Although, having said that, methanol, which is probably the fastest growing chemical, tends to be produced mainly in China, where, as I've just described, coal is a key fuel. So again, thinking about continuing to use these plants without closing them prematurely, carbon capture and storage, retrofit, or some element of fuel switching to biomass or hydrogen seems to be a good alternative, particularly in Asia. So now moving on to the role of coal and how these heavy industries can decarbonize. This chart shows really the dominance of China in terms of the production of the global products that I've just talked about. So China is producing something like 70% of, 55 to 60% of our global aluminium, steel, and cement. And coal is the primary fuel in China. So if we look at how much of that material is produced from coal, it's around 70% of China's steel is coal-based, 83% of its cement is coal-based, and 75% of the aluminium. If we then think about the electricity that's used to produce that aluminium is derived from coal. There'll be different approaches to how the fuel is used. So looking at some of the other regions, coal is less dominant. So how decarbonisation will be adopted in these regions very much depends on the availability of fuel and other local factors. Moving on now to the emissions from heavy industry. So heavy industry produces around 8 gigatons of CO2 per year of direct emissions, also called Scope 1 emissions. And this is around 23% of the total global CO2 production. If we then include the indirect emissions in that, so here it would be emissions from the electricity used in aluminium smelting, for example, this increases the impact of industry to around 40% of global CO2 emissions. Cement, iron and steel and chemicals and aluminium account for nearly 75% of those industrial emissions. So it's reducing the emissions from these heavy industries that is going to have a significant impact on how we move towards net zero, and is a significant challenge. In terms of coal's role in net zero emissions, the IEA have forecast that total coal through to 2050 could be as much as 15 exajoules, or about around 600 megatons per coal equivalent. And the majority of this is forecast to be used in the heavy industries I've just talked about. Other forecasts, for example, the DNV's Energy Transition Outlook forecasts a slightly higher amount of coal, maybe as high as 1,400 megatons of coal. And this will be produced in regions like Greater China, the Indian subcontinent, and to a lesser extent, Africa and other parts of Eurasia. Common to both of these forecasts is that coal will fall significantly through to 2050 by as much as 80 to 85%, but it will still be a significant part of how we achieve net zero emissions. And the advantage of coal is that it's widely geographically distributed, it has a relatively stable price, and it therefore increases the resilience of industry and the industrial users. Moving on now to look at the individual sectors in a little more detail. So iron and steel. Here, based on the DNV projection, coal could provide as much as 14 exajoules, or around 480 megatons of coal equivalent through to 2050. The demand will be around 50% of the current coal use levels. Again, the Energy Transition Outlook forecasts, the forecast is based on reducing the energy demand for iron and steel, increasing the amount of recycling, moving to electric arc furnace and increasing the amount of recycled scrap steel, and using direct reduced induction. But again, carbon capture and storage will be a key part of how fossil fuels will continue to be used in iron and steel. And this next chart shows how innovative technologies will be used or potentially used to decarbonize steel. So there's a wide range of technology options under development. This includes, as I've just talked about, electric arc furnace, includes switching to hydrogen and carbon capture, utilization and storage. There's around 17 families of technologies. For coal, for example, it's things like smelting reduction and fitting carbon capture and storage to the blast furnace, basic oxygen furnace approach. And the choice of those technologies will be highly dependent on local fuel prices, on the availability of low carbon electricity, and on the availability of CO2 storage, particularly for carbon capture and storage. Moving on now to cement. In a similar way to iron and steel, coal will continue to be a major part of how cement will be produced, potentially as high as 3.5 exajoules of coal, or around 120 megatons of coal equivalent, are still forecast to be used in 2050. This is based on a 50% reduction from current levels, and it reflects how coal can provide the high temperature heat, particularly for clinker production, where electrification in particular has relatively limited use. Carbon capture, utilization and storage will be a significant part of the deployment of how that high temperature heat can be produced. There's also opportunities to reduce the amount of clinker content in cement, in concrete, and also to look at reduced demand. And just to look at that in a little more detail. So this chart shows the kind of range of decarbonisation approaches that the cement industry can take. Carbon capture, utilization and storage provides the biggest chunk of that, around 36% or 1.4 gigatons of CO2 reduction per year. Other approaches, so if we look at the right-hand side of the chart there, there's an opportunity to look at recycling an element of the cement, to look at repurposing buildings and extending the life of buildings, all which can reduce the demand for concrete. And on the left side of the chart, there's also the opportunity to reduce the amount of clinker in cement, so to look at alternative cementatious materials, to look at switching to hydrogen as a decarbonised fuel, and also to think about the kind of design of cement. So if we try to match the specification of this cement to the particular application, there may be opportunities to use lower cement content in concrete, which again could reduce the demand. The next area I want to look at is chemicals. So again, coal will have a role through to 2050. Maybe as high as 2 exajoules of coal demand, or around 70 megatons of coal equivalent. Again, there's an opportunity for a range of approaches to be used. So we could look at increased recycling of materials, where plastic recycling is quite low at the moment, and there's a good opportunity to increase its use as a carbon feedstock. Can also look at reducing the demand for chemicals. So in ammonia demand for agriculture could be reduced if we look to move away from nitrogen-based fertilizers and look more towards organic fertilizers. There's the opportunity for electrification of some of the low and medium temperature process heats, and also to look at fuel switching to low carbon and hydrogen and biomass. Particularly in China, coal is used for the manufacture of ammonia and increasingly for the manufacture of methanol. So again, thinking about the dominance of China and Asia, there appears again to be a good opportunity for carbon capture and storage to be the biggest lever to achieve decarbonisation within the chemical sector. This table just kind of highlights some of the numbers that I've just spoke about. So increasing the share of recycled materials. So currently we only use about 8% of recycled plastics in chemical manufacture. So there's a good opportunity to increase that through to 2050 and reduce the need for new carbon-based feedstocks. Can also look at increasing hydrogen demand, where that's forecast to potentially double through to 2050. But it's these innovative routes that's going to provide the main source of decarbonisation. For example, CO2 capture will increase significantly from where we are today through to as high as 540 megatons of CO2 capture per year by 2050. Aluminium is the final sector I wanted to look at. So here it's the decarbonisation of the electricity supply, which is going to have the largest impact in terms of aluminium production. And this recognises the smelting process as being the main energy use within aluminium, and electricity provides around 65% of the total energy used in aluminium production. So here it's switching to renewable power and potentially fossil fuels with carbon capture and storage that's going to provide that decarbonisation of the electricity supply. Again, like chemicals and like steel, recycling of scrap material, again, should be increased as high as possible. This is really significant for aluminium, as recycled aluminium uses only 5% of the energy input as producing new aluminium from alumina. So it seems pretty obvious they're increasing the amount of consumer scrap to increase recycling rates to potentially as high as 50 to 60% should be adopted. In terms of direct process emissions, there's the opportunity to use things like inert anodes, to use carbon capture and storage in the alumina process, to think about hydrogen fuel switching and process improvements. So mechanical vapor recompression is an example of that. And the chart here just shows the reductions that those different technologies could apply to the direct process emissions. But as I said in the introduction to this slide, it's decarbonisation of the electricity supply that will be the dominant means of reducing CO2 emissions for this sector. Carbon capture and storage, I think, is a key enabling technology for heavy industries. And if we look at the impact of carbon capture, utilization and storage for manufacturing industry as a whole, it could provide 2.5 gigatons of CO2 capture, and therefore the amount of CO2 reduction needed to decarbonise heavy industries. Cement is probably the most significantly impacted of the heavy industries, largely because of those process emissions, inherent process emissions that I spoke about. But clearly it also has large roles in steel, in total chemicals production and aluminium production. CCUS is growing. I think after a few years of decline, the chart on the bottom there shows how carbon capture, utilization and storage has really started to increase in the last 2 or 3 years. Currently, we have 30 operational CCUS related projects capturing around 43 megatons of CO2 per year. The pipeline for CCUS has increased by as much as 44% over the last 12 months. So we now have potentially 196 projects with the ability to capture 244 megatons of CO2 per year based on the ICSC database. Chemicals and hydrogen feature strongly in those new pipeline of carbon capture and storage projects, and to a lesser extent cement. It's provision of transport and storage infrastructure through the hubs and clusters approach that will be a key way by which carbon capture, utilization and storage can be delivered, and to reduce its cost to move towards commercial application. I think it's fair to say that coal applications are relatively limited in that new pipeline of projects, which is something we need to address. And also, whilst this increase is good in terms of the increase in carbon capture and storage, there still needs to be significantly more done. So the trajectory is good, but to achieve the carbon capture and storage needed, there really needs to be a magnitude, a one scale of magnitude increase through to 2030, and to be able to capture the amount of CO2 needed through to 2050. Although coal doesn't feature strongly in the new pipeline of materials, there are examples of coal-based carbon capture projects in the existing operating plant. So examples are the Great Plains project in the USA, of which the carbon capture and storage element has been operational since 2000. This project produces 1,300 tons per day of syngas for the production of substitute natural gas and anhydrous ammonia to produce fertilizers. It captures 3 megatons of CO2 per year, which is transported to Canada for use in enhanced oil recovery projects. Another example is the Capital project in the USA for cement production. This has been operational since 2015 in Texas. It captures around 15% of the CO2, so 50 to 75 kilotons of CO2 per year, as a side stream in utilization of the CO2. So they're using sodium hydroxide as a scrubbing solution, and this is used to produce sodium bicarbonate, bleach, and hydrochloric acid products. And the final example I want to highlight is the Sinopec project in China. This has been operational since September of 2022. It produces 100 tons per day of hydrogen for fertilizer production, and it captures 1 megaton of CO2 per year for use in enhanced oil recovery in China. Although not strictly an industrial related carbon capture and utilization project, I particularly like this project in China, the Huaneng Longdong project, which is 10 gigawatts overall. It's due to be operational later this year, actually, and it comprises 8 gigawatts of variable renewable electricity from solar and wind, backed up by 2 gigawatts of ultra supercritical coal plant fitted with carbon capture, utilization and storage. That coal element is capturing 1.5 megatons of CO2 per year when it's operational later this year, and it will be stored in geological storage formations. And I really see this as a kind of a microcosm of how coal fitted with carbon capture, utilization and storage can support the increased penetration of variable renewable electricity and can help to provide a stable grid to provide high availability whilst variable renewable electricity increases. It's particularly useful in China, where there'll be lots of electricity needed for aluminium production through the smelting process. The final element of carbon capture, utilization and storage is the storage element. So the Oil and Gas Climate Initiative have commissioned this study on CO2 storage resource, the CSRC catalogue, which has assessed some 850 storage sites in 30 countries at the moment, and have located around 14,000 gigatons of potential CO2 storage. This level of storage would be sufficient to provide around 2,000 years of the CO2 storage that we'd need based on the 2050 projected capture rates. The CO2 stores are generally close to the emissions intensive regions. So if we look at Asia, if we look at Europe, look at North America, they all have potential storage sites. And in China, for example, around 65% of the point sources of CO2 are within 100 kilometers of a potential storage site. Most of these sites are in saline aquifers, so around 97% of them would use this means of storage, with the remainder typically being disused gas and oil reservoirs. So combined with the provision of transport and capture infrastructure, particularly using that hubs and clusters approach, there's great potential for the use of carbon capture, utilization and storage. So finally, to wrap up with some key messages. Heavy industries are a key part of how we operate. They're used to produce the key products that are used in providing our infrastructure, in providing the variable renewable electricity infrastructure that we need. But they're difficult to abate, so-called hard to abate, because of the need for high temperature heat, because of the inherent process emissions in terms of the production of the materials and in terms of the relatively young fleet. They can, however, be net zero emissions compliant through a series of measures that I've described briefly, including demand reduction, including the increased recycling materials and fuel switching to low carbon fuels, but also the use of carbon capture and storage. Coal will continue to play a key role in heavy industries, with perhaps as much as 600 to 1400 megatons of coal still being required by 2050. And the value of this coal is that it provides increased resilience to industry, and it provides the high temperature heat and fuel feedstocks for a number of the industrial processes. Carbon capture, utilization and storage is a key enabling technology to allow that coal to continue to be used. Projects should therefore continue to be deployed to reduce the cost and to establish the transport and storage infrastructure that we'll need through to 2050. I think as an industry, as organisations that advise government bodies, we need to be pushing for more coal-related heavy industry carbon capture and utilisation projects to be part of that new portfolio of projects. Because as I've described, it's really a key way of how we can decarbonise heavy industries. Finally, I'd just like to highlight this workshop that's going to take place in April of this year. So this is the ICSC in collaboration with ESCOM holding a workshop in South Africa on the 19th to the 20th of April. So please join us if you have the ability to do so. Thanks for listening. I'd just like to point out that the report that this presentation is based on will be published next month and available to download from the ICSC website. I've focused on the role of coal in terms of how the industries will decarbonise, but within the report I take a wider look at recycling and demand reduction and other means. So please take a look at that for the kind of fuller picture of how industry can decarbonise. So thanks for listening. I'll just open up the questions box now and see if there's any questions I've been asked. Right, so the first question says, hi Greg, which of the heavy industries would offer the lowest cost to include carbon capture and utilization plants? And secondly, how significant and limiting will geography be in advancing general CCUS implementation? So I think the kind of lowest hanging fruits in terms of decarbonisation will be the chemicals industry, where there's a higher concentration of CO2 streams that are most readily accessible. It's probably iron and steel and cement that will have the highest cost of CO2 capture. In terms of geography, I think I showed later in the presentation that there's a range of geographical regions where CO2 capture can be stored. So I don't foresee there being any limitations in terms of geography. It's probably the geographical regions where heavy industries are primarily based, which is China and Asia, and there is good geographical storage potential. Just scrolling down. A comment that this was a good and useful information, and can the slides be shared? So the slides will be available to download from the ICSC website. This presentation has been recorded and will be available on the ICSC YouTube channel for people to listen to later on. Currently, I don't see any other questions at the moment. But if there are any other questions that come in, then please type them in, and I'll endeavour to answer them offline. So thanks everyone for listening. I'll just hand back to my colleagues to close the conference.
Thank you, Greg. And as you said, the slides from this webinar will be available shortly from our website. And next month's webinar will be on energy security and will be presented by Dr. Andrew Minchner. Thank you all for joining us today, and goodbye.